Thank you. Thanks, Adam, for the introduction, and thanks very much for the opportunity to speak here. I've been really enjoying the series. I think it was a great idea to have this. So let me go to full screen. Okay, so you can see this okay, I hope.
Absolutely, yeah.
Good. Okay, so I'm going to be talking about Electroweak effective theories, the on-shell way. And this is work done with Yaniv Weiss, who's my student. And it's really actually thanks to him that I re-entered this subject. And he taught me a lot of what I know about it. And three other excellent postdocs, Gauthier Dourier, who's now at CERN, Tepe Kitahara, who's faculty at Nagoya now, and Camila Machado, who's at DAISY. Okay, so the main idea here is to develop an on-shell approach to EFTs. And I was very happy to have this spelling out of the acronym, because I was really trying to get rid of the field theory here. So this effective theory is due to these guys in a recent paper. And so we want an on-shell approach to EFT extensions of the standard model. And there are going to be two main themes in this talk. So one is a toolbox for EFT computations and analysis. And the other one, as we'll see, is trying to develop an on-shell understanding of Electroweak symmetry breaking and the Higgs mechanism, and sort of relearning things that we know from field theory in this way. So I was asked to say which EFT I'm going to talk about. And as you'll see, part of this is really about tools. So these are general tools that you can apply to the EFT of your choice, whether it's the standard model plus something, or whatever else you're interested in. And the main focus here is going to be applications to the Electroweak theory. And when we talk about the Electroweak theory, then we're really talking about any EFT with the Electroweak particle content. And in particular, if you were interested in the SWIFT, then you can impose SU2 times Z1 at high energies. But if you don't do that, you are basically looking at all sorts of different EFTs. And because we're taking a bottom-up sort of bootstrap approach, we can in principle explore very general extensions of the standard model, whether they're weakly or strongly coupled, and we'll talk some more about that. Okay, so this is my outline. I'm going to start with some motivation for why we want to go on shell. Then I'll talk about some amplitude essentials that we need. So we had an excellent introduction by Henriette, and we also had another talk by Lian Tao. So I'll build up on that. The main new ingredient that I'll need are treating massive particles. So I'm going to talk about the connection between massless and massive spinors, the high energy limit, and bolding and unbolding. And then once we have all these tools, I'm going to show you some warm-up examples of how this construction proceeds, just to get the general idea. And then we'll turn to the Electroweak EFT. So there we'll consider some examples. We'll look at the high energy behavior of some massive amplitudes and talk about their high energy limits and the relation to perturbative unitarity, and see some elements of the gauge symmetry emerge and of Higgsing. And then in the last part of the talk, I'm going to turn to basis, which is how we construct bases for these amplitudes, and talk a little bit about that. So just before we start going into details, I want to sort of give you a very broad picture of what's the current toolbox that we have for these massive amplitudes. So we have general 3- and 4-point amplitudes of massive and massless particles of various spins. In particular, for the Electroweak theory, we have everything that we need, 3 points and 4 points for spins, the spins that we have in the Electroweak theory. We have a detailed prescription for how to glue together amplitudes. And as I said, basis for all the massive 3 points, basis for all the massive 4 points. And these are bases that span either generic amplitudes or contact terms only. And we also have the matching to the broken phase SMIFT for 3-point functions and one example of a 4-point coupling, which kind of tells you how to do that if you were to extend this matching in general. So basically at this point, you can really play with this and apply this to other 4 points of interest, and the extension to higher points is pretty simple. Okay, beyond the Electroweak theory, we also have bases for all the massive 3 points for higher spins up to 3, and some and more results for 4 points that are, I'm not going to read them out, but they're listed here. Okay, so the main reason we're all here is that at this point we're completely ignorant about beyond the standard model and whether it's there at all. There are no hints from the LHC. We haven't discovered any full UV extension of the standard model in full glory, as people used to expect. And in particular, that we don't understand the origin of electroweak symmetry breaking and the naturalness problem. So with this ignorance acknowledged, it's a very natural thing to turn to EFTs, and in particular bottom-up EFTs. And essentially what these provide is a well-defined framework for quantifying this ignorance. So essentially what we want to do is parameterize our deviations from the standard model. So in the usual construction, when you look at what's the input to these theories, these are the standard model fields, possibly some beyond the standard model fields, the standard model symmetry, namely the global and gauge symmetry, and of course Lorentz and locality. And out of this comes the most general Lagrangian. So we have an expansion, some higher dimension operators, suppressed by appropriate powers of the high scale lambda. Now, for this reason, the bottom-up on-shell approach is very natural because it really does the same sort of thing. The input in this case are the standard model particles, possibly some new particles. The symmetry, in this case, it's mainly the global symmetry. You don't necessarily need to impose the gauge symmetry because it will emerge, and also Lorentz and locality, and out come the most general amplitudes. So starting with the most basic amplitudes, the 3-point amplitudes, you can glue them together into higher point and higher order amplitudes. And as I said, the gauge symmetry can emerge from the requirement of having consistent interactions of spin 1 particles. Okay, now the first step of the EFT construction is, of course, to identify a basis of operators. So you want a complete basis and an independent basis, modulo the various field redefinitions, the use of the equations of motion, gauge redundancies, and all these things. And that's not an easy problem. Mathematically, it boils down to the problem of finding polynomials of operators subject to a set of constraints. And that was beautifully solved using the Hilbert series methods. But in an on-shell construction, a lot of this gets very simple. So in an on-shell construction, you only deal with physical quantities. And so this first step is mostly circumvented. You don't need to worry about field redefinitions or gauge redundancy. Instead of polynomials of operators that are subject to a set of constraints, like the equations of motion, this problem really maps to polynomials in the Mandelstam invariants. So instead of talking about polynomials of operators, here we're talking about simple polynomials in simple numbers subject to a set of kinematical constraints. So such as s plus t plus u equals the sum of the masses squared. So as a byproduct, one thing that you get out of this is a simple counting and classification of the EFT operators. Okay, now for standard model applications, you usually start from this EFT Lagrangian with a full SU2 times U1 symmetry. And once electroweak symmetry is broken and you want to include that, these different operators modify the various couplings that you have in your Lagrangian, including the masses, the standard model couplings, and so on. And so you need to redefine your input parameters, including the standard model ones. In an on-shell construction, you're just relating physical observables. I say largely because some of the 3 points are not completely physical. And so you're relating things that are directly measurable. So this offers, in principle at least, a simple way of relating different observables and fitting to experimental results. From the point of view of computation, you, of course, avoid Feynman diagrams, and these are particularly complicated with EFT vertices. Okay, so the question really is, at this point, how on-shell do you want to be? Do you want to go fully on-shell, or can you be half on-shell? And in this case, you can be half on-shell, and it's very useful. You can work in the unbroken electroweak symmetry phase and impose the full SU2 times U1 symmetry. So in that case, you're doing on-shell computations in the unbroken theory with massless particles only. And this is, of course, a good approximation at high energies. And this is all you care about for running, for computing anomalous dimensions, and so on and so forth. So that's the approach that's been mostly used and has yielded many, many powerful results, including classification of operators, selection rules, operator mixings, anomalous dimensions, positivity, and I'm only mentioning some of the relevant papers here. But the focus here is going to be fully on-shell. So we want to work with the standard model particles, namely the actual W, Z, Higgs, and all the rest of them. And in doing that, exploit the full power of the on-shell approach to relate purely physical observables. And to some extent, this is also motivated by the ignorance that I talked about before. It's kind of nice to go back to basics and just work with the things that we know are there, like the standard model particles. Okay, so the first thing we need is to develop some tools that we're going to use. So let me quickly review some basics. And the main approach is going to be this. The little group and spin statistics are going to determine all the endpoint contact terms, starting with n equals 3. The remaining parts of the amplitudes are determined by factorization or by generalized unitarity. And so you can essentially, starting from the 3-point amplitudes, bootstrap to higher point amplitudes by gluing together 2 lower point amplitudes. And after doing this gluing, you also need to add the contact terms. So you do this in stages, you derive all the 3 points, then you get the 4-point amplitudes by gluing to 3 points and adding 4-point contact terms, and so on and so forth. Now, these contact terms correspond to the EFT operators. They come, of course, with unknown coefficients in the amplitude, and these are precisely the analogs of the Wilson coefficients. So, of course, the 0th order task that you have in this game is to find the contact terms. Now, I think I'm pretty sure that most of you have seen the massless spinor formalism, but let me quickly go over it anyway. So we can write amplitudes in terms of massless spinors. And essentially what we're using is the fact that momenta can be written in terms of massless spinors. And the same holds for external polarizations. So obviously for fermions, the external polarizations are just massless spinors. And for spin 1 particles, you can write the polarizations like this, where this is the momentum, and this is some reference momentum. And so putting these all together, the amplitude is written in terms of these products of massless spinors. Once we have that, we can really use the power of the little group. For a massless particle of momentum k, k is invariant under the little group, which is the U1 in this case, but the polarizations are not. So if we assign little group charge 1, for example, to this angle spinor, then the square spinor has the opposite charge. The polarization, the positive polarization has charge +2, and minus that for the negative polarization. And as a result, we get selection rules. The helicities of the external particles determine the little group weights of the amplitude. So just to, it will be useful to bear in mind that each massless fermion has one spinor I, whether it's square or angle. So if you hear kids yelling in the corridor, it's not my kids, I'm in the office, but it's some kids still yelling in the corridor. Okay, if you have a massless vector, then there are two such spinors, either two squares or two angles. Okay, now let's go to massive amplitudes. So there's a very nice formalism introduced by these guys, which is little group covariant. And here the idea is that you split each momentum in terms of two massless momenta. So we call these P1 and P2. This index I labels takes the values 1 and 2. And the little group of the particle with momentum P rotates these guys, rotates between P1 and P2, the P1 and P2 angle spinors, and similarly the square spinors. So momenta are written in this way. The massive fermion polarizations are obviously written also in this way. It's we have a Dirac spinor made up of an angle and a square spinor. And for spin 1 polarizations, the polarization is also expressed in this way. So here, choosing I and J to be 1 gives you a plus polarization. Choosing them to be 2 gives you minus polarization. And choosing 1 and 2 gives you the 0 polarization. Now these spinors are bolded here, and this bolding denotes symmetrization over the little group indices. So whenever we have bolded spinors, it means that these little group indices are symmetrized. And just for convenience, I'm going to also use boldface to denote any massive momentum to distinguish them from massive momenta, from massless momenta. Okay, so amplitudes are expressed in terms of these spinor products at the end of the day. Some that are angle, some that are square, and possibly we have momentum insertions inside. And again, in this case, each massive fermion comes with one square or angle spinor, and each massive vector comes with 2 of these guys. Okay. More generally, you can write a spin S representation as a symmetric combination of 2S of these spinors. Okay, so why have we suffered through this? With the amplitudes written in this way, first of all, we can use the power of the little group. Now, instead of having U1 selection rules, we have selection rules coming from the SU2 little group. And there's also a beautiful connection between the massive and massless amplitudes via simply unbolding or bolding the spinors. And in order to see that, let's look at the high energy limit. So when we split the momentum like this, choosing the direction of, let's say, P1 amounts to choosing the spin polarization axis. And if we want to recover helicity states and helicity amplitudes at high energies, we want to align this guy with the massless limit of P. So we can make this choice of momenta. So this guy goes to 0 as the mass goes to 0, and this guy coincides with the momentum. So in the high energy limit, if we have a vector of positive polarization, so I and J are both 1, this combination reduces to KK, which is what we have for a massless vector, and everything else vanishes. Similarly, a vector of 0 polarization in the high energy limit goes to this combination, which has little group weight 0, and so looks like a scalar state. So you get the massless amplitude simply by unbolding these massive amplitudes. And as we'll see, in some cases, you can also do the inverse, namely start with massless amplitudes and bold them to get massive ones. So let's put this to work. And I'll show you 2 simple examples. So here, for example, is an amplitude, some scalar plus 3 gluons. So the scalar is a standard model singlet. It's got spin 0, and I'm just going to look at the all plus helicity amplitude for the gluons. And here the little group tells you that you have to have this spinor structure where 1, 2, and 3 label the gluons. And this holds up to some function of the invariance. Now, if we just look at the contact terms, there are no poles. So the only thing that can multiply these guys, this guy is some polynomial of the invariance subject to this kinematic constraint. So that's the general form of the amplitude. So I have the spinor structure out front and then an expansion in the invariance. So here I'm showing this for dimension up to 13, but you see that it's completely trivial to extend this. You just need to write polynomials in the SIJs that are either symmetric or anti-symmetric, depending on whether it's multiplied by FABC or DABC. And this is basically the derivative expansion. Now, adding in the factorizable part from gluing to 3-point amplitudes brings in this term here, and that's the end of the story. And then you can map these different terms that you saw there into operators feeding in to this all plus helicity, and you recover the result that you expect from the operator point of view. You can do the same thing with a vector instead of this scalar that I had before. And again, I'm showing one example. So it's the same story. The little group determines these red spinor structures, and they're multiplied by some polynomial of the SIJs. And here I'm showing this going up to dimension 12, but it's very easy to go beyond that. And to take the high energy limit and get the massless amplitudes, all you need to do is unbold this and get the different amplitudes for positive, negative, and 0 vector polarizations. Okay, so these were some examples, and let's now turn to Electroweak EFTs. So the first thing we need, as we said, is we need bases of massive spinor structures which span either the generic amplitudes or just the contact term pieces. Now, for 3-point amplitudes, this paper by Kanihamed, Wang, and Huang gave a construction of all the massive 3 points, but this gives bases that are generically overcomplete. So one thing that we did was to derive independent bases for the Electroweak 3 points, and beyond that for spins up to 3, and also for 4 points. So I'm going to come back to discuss the bases towards the end of the talk. But before we do that, let's start by looking at a few interesting amplitudes of these electroweak particles. So the first guy I want to look at is the WWZ coupling, because it's the basic coupling that you're interested in when you're talking about the gauge symmetry. So we have three particles that interact that are nearly degenerate. So just to make things a little simpler, let's, for starters, forget the mass difference between them and neglect that. And I want to look at this coupling and see what we learn from that. So if you neglect the mass difference between them, the most general amplitude that you can write down is this form. And if you look at this, it's completely symmetric under the exchange of 1, 2, and 3. So to write something with the correct statistics, we need to have, I'm sorry, it's completely anti-symmetric. So to write, to get the correct statistics, we need to multiply this by some prefactor that's completely anti-symmetric. So therefore, we have to have an epsilon ABC here. So you see that the SU2 structure emerges completely automatically. And if you had n degenerate particles instead of 3, then this epsilon ABC would be replaced by some completely anti-symmetric tensor. In order to see the full Lie group structure, you need to go beyond this and look at 4-point amplitudes, and that would give you the Jacobi identity. Now, if you know the massless analog of this, you see that this massive case is actually even nicer than the massless case, because all the different gauge bosons are on the same footing, and it's very easy to see the symmetry properties of the coupling. Okay, we can also see electromagnetic charge conservation from this. Again, because this is fully anti-symmetric, before we put in the epsilon tensor, it vanishes for identical W's. And so an amplitude of the type W plus would vanish. You could also say more and see the full SU2 times U1 structure if you consider the high energy limit and look at some combination of the WWZ coupling and WW photon coupling. Okay, now let's talk a little bit about renormalizable versus non-renormalizable terms here. So there are a bunch of terms appearing in this amplitude, and I chose to normalize them differently. There's 1 over m squared here, and 1 over lambda bar squared here and here. And the reason for this identification is basically considering the high energy behavior of this amplitude. Of course, when you're talking about the high energy behavior, you're looking at the massless limit of this amplitude, and there your 3-point amplitude is on shell only for complex momenta, but we can simply think about complex momenta. So at high energies, these blue structures scale like m squared times e, and that means in particular that they have a smooth limit even if we include a 1 over m squared. So from the fact that they scale with the energy, we can conclude that they're renormalizable. On the other hand, the red structures here scale like e cubed, and these guys require a cutoff. They require a 1 over lambda bar squared normalization. So essentially what we're doing here is we're saying order E is good, order E squared or higher is bad and requires a cutoff. And that's really a 3-point version of perturbative unitarity. So if you think about the 4-point amplitude, it scales like 2 powers of the 3-point amplitude with a propagator that goes like 1 over E squared. So you see that the 3-point amplitude can grow like the energy, but any E squared requires a cutoff. A completely equivalent way to say this is to say that you want a smooth behavior when the mass goes to 0. So E over M is bad, but E over lambda is good. And so implicitly, I'm assuming here some hierarchy between M and lambda, because I'm imagining that I have a good limit and a well-behaved and smooth theory when above M and below lambda. One thing I forgot to say is that I denoting the scale here by a bar, just to stress that this is the EFT scale in the broken phase. Okay, so one thing I want to note here is that these 3-point amplitudes are exact expressions. The kinematics is fixed. Any dot product of the momenta is determined by the masses. And so in matching to the field theory computation, these coefficients really sum all the loop orders and all the terms in the V over lambda expansion. So the result that you get is completely general. Okay, now let's turn to a different example with two fermions coupling to the Z. And in this case, this is the most general amplitude you can write down. There are 4 terms here. There are 2 terms that I denoted in blue because, again, I'm associating them, I'm identifying them as the renormalizable ones. These scale is M times the energy at high energies, whereas these guys scale is E squared. So these come with a 1 over lambda. And there are many things that we can learn by looking at the high energy behavior of this amplitude. So if we require a smooth high energy limit of the separate helicity amplitudes, we'll find many things that we're familiar with from QFT. I'm not gonna go over them in detail, but I'll just show you one in particular. So looking at this particular helicity amplitude at the high energy limit, it goes like GL minus GR times the fermion mass divided by the Z mass times this spinor product. And so you see that for this to be well behaved, as MZ goes to 0, either GL minus GR vanishes, in which case you have a vector like fermion, or the fermion mass needs to go to 0 as the vector mass goes to 0. So if you have a chiral fermion, you see that its mass has the same origin as the vector mass and needs to go to 0 at least as fast. And this is something that we'll refine in a bit when we talk about the 4-point amplitude. Okay, so let's look at the last example, one with a fermion Z and the Higgs. So there's first of all a factorizable part where we glue together the 3-point amplitudes. So this features all the 3-point couplings that we saw before. Plus there are 4-point contact terms. So these are the contact terms in this case. Again, these guys are completely determined by the little group up to some coefficients. And the coefficients, again, are given as expansions in the SIJs. And again, in this case, the expression that we have here captures all orders in the V over lambda expansion. So the coefficients contain the derivative expansion, but the spinor structures here contain all the V over lambda expansion. Again, we can look at the high energy behavior of this amplitude and require good high energy behavior. So here we have we can really talk about perturbative unitarity because this is a 4-point amplitude and we can look at its energy growth. So any terms that go like E have to be suppressed by the scale lambda. And so that gives us a relation of this form. So here we have GL minus GR times this factor here, which needs to vanish up to corrections of order M over lambda. So again, we see that for a vector like fermion, GL equals GR, there is no constraint on the mass. But for a chiral fermion, we get a specific expression for the fermion mass, namely that it's equal to the Yukawa divided by the gauge coupling times the Z mass. So we see how the fermion mass emerges from the, just like we expect from the Higgs mechanism. And by the way, here, one thing that I assumed was that we have a single Higgs, just like in the standard model. If we have more than a single Higgs, then this result is going to be modified. Okay. So one thing that I already used here, and we need to use in general, is some bases to span the different amplitudes. And so let me talk about that. I'm going to be a little sketchy because it's fairly technical. But if you want the details, you can find them in our latest paper, or you're welcome to ask me about it. But I'll at least, I at least want to show you how things work. So there are three types of bases that we were interested in. The first one is sort of the most, the first thing that comes to mind, which is something that we call the spinor structure basis. So that's just the minimal set of spinor structures, SI, that span the amplitude. So by this SI, I mean a product of things like these spinor products. This I labels all the little group indices collectively, and there are no prefactors of the invariant Sij. Now, this is a question that you can ask in different contexts, obviously, and people have looked at ways to write the amplitudes in terms of the usual polarizations and momenta, and so on and so forth. But here we're interested in a basis in terms of these massive spinors. So essentially what we want to do is get rid of a structure and declare that it's redundant if it can be written as a linear combination of other SIs, other spinor structures, with coefficients that are some rational functions of the invariance. Now, the number of elements in the basis is known. It's given by simply the product of 2 SI plus 1 for each one of the external legs. And in general, to test whether two structures are independent or not, or a bunch of structures are independent, you can construct inner products of these spinor structures. So the inner product of S1 and S2 is given by this, and it's equal to some function of the invariance. Okay, now we're interested in EFT amplitudes, so we're really interested in the contact terms only. And in particular, that means that there are no poles in this part of the amplitude. So we want to get a manifestly local amplitude, and we don't want to have any negative powers of the invariance show up. So in order to find a basis for this part of the amplitude, a structure is redundant if it can be written as a linear combination of the other structures with coefficients that are polynomials of the invariance, as opposed to rational functions. So now I just don't want to have any negative powers of the Sij's appear. So if I have a basis of this type, this is something that I'm going to call the stripped contact term basis. It's just the minimal set of spinor structures of this type. And the stripped here just means that there are no Sij's multiplying them. Once I have a basis like this, it's very easy to construct the contact term basis. You just take the elements of the SET basis and you multiply by Sij's. So let me give you some simple example to demonstrate, to illustrate this. So let's take a massless 4 fermion amplitude with all plus helicities. The spinor structure basis has just one element, this guy. and it spans the generic amplitude. So I can write this 1324 guy is this 1423 up to this ratio of invariance. And the Schouten identity allows me to write this combination in terms of these other two. However, if I'm interested in the stripped contact term basis, I really want to keep both this guy and this guy, because I don't want to allow negative powers of the invariance. So to spend the contact term EFT amplitude, which is manifestly local, these are the things that I need. Now, from these two guys, I can get the full set of contact terms. I just need to add these guys, to multiply these guys by some Sijs. So at dimension 6, I just have these two. At dimension 8, I have S13 times this, S14 times this, blah, blah, blah. But for instance, this guy, S14 times this one, does not appear because it's not independent as a result of this identity. Now, the massless case is very easy. It's very easy to construct massless helicity amplitudes. So it really pays to try and extract as much information out of that as possible. Oops, okay. And in order to do that, we can classify the massive spinor structures according to their helicity categories. So namely the helicities of the high energy limits or unbolded versions. So for example, in this fermion-fermion vector scalar amplitude, the helicity category of this guy is plus plus 0, plus 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 0, because everything is square bracket, and here 1 is positive, 2 is negative, and 3 is 0. And in general, the number of helicity categories that you have is just this product of 2s plus 1, which is exactly the dimension of the spinor structure basis. Now, another thing that we need to know is that in the massless limit, spinor structures of different helicities have vanishing inner products, so they're independent. So that gives you a very simple prescription for getting the spinor structure basis. You just take the massless amplitude in each helicity category and bold it, and that will give you the massive basis. So the reason this works is that this bolding essentially means that you're starting with the massless amplitudes and covariantizing them with respect to the massive little group, namely the full SU2. And it's actually useful that if you add extra scalars, this doesn't change the basis, because they you don't need any new structures to span them. So this gives you a simple prescription for finding basis for not just the 4-point amplitudes, but also any additional scalars on top of that. Okay, so so far I talked about the spinor structure basis, but as we said, we're mainly interested in EFT amplitudes, so we need these stripped contact term basis. In this case, it's not as simple. We can't just start from the massless case and bold it, but we can still use many elements of the massless limit. So one thing that's very useful here is that each massive spinor structure identity comes from a massless spinor structure identity. So for example, here is a massless identity. You can get it very simply by just noticing that this 1, 2, 3 structure can be written like this, and then using some identity. And so this is an identity between two massless structures, and its massive version or bolded version is just this. So it holds when you bold the identity up to some mass corrections. And specifically in this case, this is the mass correction. but very often you don't really need to know what the mass correction is. So you can just start from the massless identity, which is very easy to find, and bold that. And another thing that's very useful is that if a spinor structure is redundant in the massless case, it's also redundant in the massive case. And so again, you can just consider its unbolded version. Okay, so there are many things that you can do based on the massless amplitudes. There's a final stage of reductions that you need to do at the end of the day, which really relies on some massive information. So as I told you, we don't allow any negative powers of the invariance in spinor relations, but we do allow negative powers of the masses when longitudinal vectors are involved. So for example, when I wrote down this amplitude, I used this type of spinor identity, where you see that over here, I have a vector, the vector 3 has one angle and one square, so it's zero polarization, and it comes with a 1 over m in the denominator. So in principle, when we have longitudinal vectors like this, negative powers of the mass can appear. So essentially the rule is that when then we have this type of combination corresponding to a longitudinal vector, it can be accompanied by a 1 over m. There are different ways to see this. One is that a massive polarization is precisely of this form. So when you take this m into account, you correctly identify the dimension of the operator. Another one to see this is more field theory based. These are essentially, if you're talking about some Higgs theory, these are precisely the Goldstone amplitudes. So they come with a p, and for dimensional reasons, I want to divide that by m. In the massless limit, this p is given by this combination of spinors. And if I covariantize this with respect to the massive little group, that's the combination that I get. So that's the source of this combination over here. Okay, so I showed you just a very sketchy picture of how to obtain these bases. There are also other methods that I didn't talk about, but basically doing this, we've derived the basis for all the 4-point amplitudes of the Electroweak theory. And these include all dimensions, basically. I mean, of course, on top of the spinor structures, you have the polynomials of invariance, but these are the simple parts. There are also similar results for massless amplitudes going to all dimensions. And one thing that I mentioned already is that there are bases for all the 3-point amplitudes for spins going up to 3. So these are the results for the 4-point amplitudes that you need for the Electroweak theory. I'm not going to go through them, but just to give you an idea of the list. It's not a huge list. This is everything that you need. And that brings me to my conclusions. So as I try to argue, this on-shell approach is very natural for constructing bottom-up EFT extensions of the low energy standard model. You basically write down all possible couplings of the standard model particles that are consistent with Lorentz, global symmetries, locality, and unitarity. You get compact analytic expressions for the amplitudes, which sum all the entire V over lambda expansion. And it's very easy to go to very high orders in the derivative expansion. The non-trivial part is the spinor structure, but once you have that, the rest is very easy. You can see some of the SU2 times U1 structure and the Higgs mechanism emerge in this way, essentially from the Lorentz structure plus the unitarity and good high energy limit for V that's hierarchically smaller than lambda. And it's truly bottom up. So you can explore extensions beyond the Smith and extra Higgses or new particles and things like that. Now, it would be thinking of thinking ahead. One thing that would be very nice to do is to obtain a systematic derivation of these stripped contact term bases for higher point amplitudes. We don't have an algorithmic way to do that. Another thing that would be interesting is to make progress on massive recursions. There has been some work on that, but it would be nice to have a fuller picture in terms of these massive spinors. It would also be interesting to include loops and running, which is something that we haven't done. And part of that should be not so hard, because essentially for the running part, all you care about is the massless part. And so by just looking at the high energy limits of the amplitudes, you can incorporate that. And another direction that would be interesting to think about is using this to do some global analyses of experimental results in terms of these on-shell quantities. So I think I'll conclude here. And since we're approaching the holiday season, I'm going to leave you with this Christmas tree table of all the 3 points for spins going up to 3 that you may want. Okay.